Alrighty, alternating series test. We know to use this when we see that -1 raised to the n or -1 to the n plus 1, and there are some other renditions again, but this is mostly how you're going to see it. And just remember that we're going to pull that -1, that thing that alternates the series out, right? And you need to show that. You need to show the grader what you're doing and take the limit of what's left, right, of what remains. If the limit equals 0, then we say the series converges by the alternating series test. So, nice and simple here. This is my series. I realize it's alternating. I pull out the alternating part and I show the grader. I'm looking to see what this thing does. I take the limit of that. Now don't forget that this is 1 to the n, which is always 1 over 2 to the n, right? To make my limit easy. And when I plug in the infinity, I have 1 over infinity, which is 0. So I can say that this series converges by the alternating series test. Now, you don't have to do anything else unless you're asked, is it conditional or absolute convergence? And in that case, then what you're going to have to do is show the grader that not only did you do this, but now you're going to take the absolute value of what's in there, right? And you're going to test that. And what happens is if I go ahead and write this out and then I take the absolute value, then what I have is this. I don't have an alternating series anymore. What I have is a geometric series, right? A number raised to the n. And my r is 1/2. That's my common ratio. And if I take the absolute value of that, which is a no duh, right? It's less than 1. So I know that's going to converge by geometric series. So, since I have converge up here when I pull that alternating part out, and I have converge down here when I leave it in and take the absolute value, then I can say that this converges absolutely. Here's another one, right? If I just asked, does it converge or diverge, all I need to do is pull this out and take the limit. And if it equals 0, I'm done. If it doesn't, I'm done, right? So, I don't have to do any other work. So I pulled it out. I have this thing here. I take the limit. I get a 0. Yay. I say this converges by alternating series. If I'm asked, does this converge absolutely, then, well, I put the absolute value symbol around for the grader. I apply the absolute value. -1 to this thing is going to become a +1. So what I'm left with is this right here, right? And I'm going to use a limit comparison test because it's easy, right? Take the biggest thing on the top, biggest thing on the bottom, and provide the grader with my b sub n. That reduces to a divergent harmonic or p series, right? And then I take the limit of the ratio of a sub n to b sub n, which is the limit of the product of a sub n times the reciprocal of b sub n, and I clean it up. Well, look, I have n cubed on top, n cubed on the bottom, so the limit is the ratio of leading coefficients, which is 1, right? And so what this does is guarantee to me by the limit comparison test that this series here is going to do whatever this series does. So in this case, this condition that I imposed is going to diverge. So we have converge, diverge, and so I say that this thing converges conditionally. That's it. That's just the extra examples I have.